Hi scholars, I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day, we care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. All right, so let's go back thousands of years ago and think about why numbers were likely invented. The first numbers that were used were the counting numbers, right? 1, 2, 3, 4, and so on. We can also call counting numbers natural numbers because they come naturally, right? So these are examples of natural numbers. And if we say how many natural numbers are there, how many counting numbers, if we sort of took them all and put them in a bag, right? If we can imagine doing that, the answer is there's an infinite number, right? Because if you give me any natural number and you say this is the last one, I can easily create one more just by adding 1 to it, right? That's how we move from the natural numbers. We just add 1 from one number to the next. So likely the first operation that was discovered or invented was addition. And addition is a way to group objects. So for example, if I have 6 sheep, you have 10 sheep, we say together, how many do we have? We can use addition to say that together we have 16 sheep. So let's take a closer look at this very simple arithmetic equation. So 6 right here, this is a natural number. So let's just use NN as to abbreviate. 6 is a natural number. 10 is a natural number. And 16 is also a natural number, right? So notice that we took these two natural numbers, 6 and 10, and this one operation here, addition, right? And we ended up with another type of that same number, another natural number. So when you take two kinds of numbers and operate on them and you end up with the same kind of number, it's like they're all like the same animal, we call that property closure. We call it closure, and we could say that the natural numbers are closed. We use that term, they're closed under the operation of addition. So let's take this idea out for a test drive. So we're being asked to create an example to support the claim, and a claim is just a statement that could be true or false, we don't know. So we want to support the claim that the natural numbers are closed under addition. Well, we just did that, right? Our example was 6 plus 10 equals 16, and we said they are closed because that's a natural number, that's a natural number. The operation we're using is addition, and so is this one. So you could think of any examples here, right? 2 plus 3 is 5. They all work. All right, so let's take a minute and think about this. Are natural numbers closed under multiplication? Why or why not? And we could even take our same two natural numbers that we've been working with, right? So we've been working with 6 and with 10. And in this case, we're going to not add them, we're going to multiply them. And that's a natural number, that's a natural number. The question is, what kind of an animal do we end up with? We end up with 60, which is also a counting number, right? So the answer is, in this case, that this is an example that supports the claim that natural numbers are indeed closed under multiplication. So the answer is here, is they are. Now I just want to be a little clear here. We have to be a little careful. Just because this is one example that happens to work, it doesn't prove that the natural numbers are closed under multiplication. This is just an example that supports the argument that they are, right? So this is an example that it is true. Yes, you end up with a natural number. In order to prove it, you'd have to multiply all possible combinations of two natural numbers and see, do we always get a third natural number, right? Which, as we know, there's an infinite number of natural numbers anyway, so it wouldn't really be possible. So we have addition, we have multiplication. So there are a few different ways of sort of thinking about multiplication. One way is as repeated addition, and this is likely what you saw in elementary school. So for example, if you have one group of these three dots right here, there's three of them, and four of those groups is going to be, right, 3 plus 3 plus 3 plus 3, so 3 4 times, repeated addition. So we have 3 times 4, right? That's one way to interpret 3 times 4. Another way is through an area model. If you have a rectangle that is, say, 3 feet high, 4 feet long, we would say that the area of the rectangle is just 3 times 4. So in this case, it would be 12 units, could be feet or meters or inches, 12 units squared, of course, because we're multiplying units by units. And the third way of thinking about multiplication is this idea of scaling by a factor. And this shows up in a lot of different areas of math later on. So for example, if you have a length that is 4 feet long and we stretch it, we can imagine putting your hand on one side, putting your hand on the other side, and sort of stretching it out so it's 3 times the length. We can call that, we say that we have stretched it by a factor of 3. And this new length right here, 4 units stretched by a factor of 3, that new length is of course going to be 12 units as well. So now that we have these natural numbers and we have these two operations, addition and multiplication, it allows us to decompose numbers, natural numbers. And decomposing, it just means to sort of to rewrite them in a different way. So let's look at a couple examples of different ways we could decompose the number 18. So we could write that 18 equals 3 times 6. Yeah, you betcha. We could write that 18 equals 3 times 4 plus 2. And here we just really decompose 6 as 4 plus 2, right? We could write 18 equals 3 times 4 plus 3 times 2, right? And all these are correct, right? Because that's 12 and that's 6. And to go from actually line 2 to line 3, this is just an application of the distributive property, right? So we did 3 times 4 and 3 times 2. So these are 3 different ways. Let's keep going. We could also write 18 as 12 plus 6. You bet we can, right? That's just moving from here to here. 3 times 4 is 12, 3 times 2 is 6. We could write 18 as 12 plus 1 plus 5. Decomposing 6 again in a different way. And finally, we could write the 18 as 2 times 4 plus 5. 2 times 9 is in fact 18. So the question is, we have 6 different ways of decomposing the number 18. Which 2 are most similar? So take a minute and think about that. Okay, and the answer that we're looking for, I mean, so there could be many possible answers. The question is a little vague, right, or most similar. But what we really want to think about is the form of these decompositions. And so let's take a look at this one right here. And let's take a look at this one right here. And notice that both of these, so we can rewrite them here. So 3 times 4 plus 2, and we have 2 times 4 plus 5. Do we see how these are actually decomposed? They have the same form because we're basically taking a number, right? We're multiplying it by the sum of 2 other numbers, okay? So they have the same structure. The structure here, if we wanted to sort of generalize it, we could say it's A times B plus C, right? They're all, those 2 are in that same form, okay? So the definition of, roughly speaking, the form of an expression is, we can say it's the way that the expression is put together, that the expression is put together. Okay. All right, let's keep going. All right, so example number 1, let's rewrite the integer 30 in the form of a times b plus c. So there are many different ways to do that. One way could be 3 times 6 plus 4, because, right, that's 10. 3 times 10 is 30. You can think about other ways to do it. We can rewrite the integer 30 in this form. Well, I could even keep our 3 here and say 3 is actually 1 plus 2 times 6 plus 4, right? That works as well. And let's rewrite it in this form. And again, there's many, many different answers. So I could do 3 times. We could go 5 plus 2, right? So let's see, what is that? 7. 3 times 7 is 21. Plus 9 will give me 30. So many, many different ways to decompose integers. Again, the key idea here is that we want to pay attention to the form. It seems rather trivial now. We're talking about just counting numbers, just natural numbers. But paying attention to form, it does play a very important role later on when we get into, say, factoring quadratic expressions, solving quadratic equations, even thinking about the structure of algebraic expressions and equations, which is definitely necessary for higher level math, including calculus in college. So this is sort of our first foray into thinking about how we can look at different forms, different ways of expressing numbers, variables, and so forth and so on. Okay, let's keep going. So by now you might be thinking, so what? What does this matter? Who cares if natural numbers are closed under addition or how I can decompose things? Let's take a look at this question. So we know the natural numbers are closed under addition and multiplication. So addition, yes, and multiplication, yes. Our natural number is closed under subtraction. So same question, and to give an example to support your claim. So take a minute on that. See if you can see if natural numbers are closed under subtraction. Okay, and one way, right, to sort of think about this problem, to start the problem, is try an example. So let's take the numbers we started with at the beginning, 6 and 10, right? So if I go do 6, well here, why don't we start here? If I do 10 minus 6, right, because we're talking about subtraction, equals 4, let's take a look. What do we have? We have a natural number, we have another natural number, and a third natural number when I subtract them. So this example right here supports the claim that, yes, seems like natural numbers are closed under subtraction. Well, let's see what happens when we reverse the order of what we're subtracting. So instead of 10 minus 6, what about if I did 6 minus 10? Right? What the heck does that equal? Okay, well, again, we do have a natural number. We do have a natural number. We're subtracting them. And when you subtract them, what do you get? Well, you get negative 4. So the question we want to ask ourselves, is this a natural number? Not a natural number, right? This is not a natural number. This number, negative 4, is not a counting number. I can't say, oh, how many books did you read last week? Oh, I read negative 4 books, right? I can't count anything. It's a negative number. And so just by using a simple operation, subtraction, that we've known since first grade, and using simple numbers, we are able to create a new kind of number, okay? And so this kind of number, let's take a look at our original counting numbers. So we had our 1, 2, 3, right? So this number, so this is our original set of just counting natural numbers. The negative number is saying, well, wait a minute, we can go forever in this direction, right? We can also go forever in this direction. So before 1, we have 0. And by the way, it took thousands of years for people to even think of 0 as a number. So that was actually very difficult. But even beyond 0, oh look, actually I have negative 1 here. I have negative 2 here, right? And so forth and so on, all the way on this end to negative infinity, right? So we have this whole set of numbers that is larger, right? In one sense, it's larger than just the natural numbers, right? The natural numbers were just part of this set, right? So these are the natural numbers, and we call this whole set, we call this, all of these numbers integers, okay? So the answer to this question, are natural numbers closed under subtraction? The answer is no, they are not. And in fact, this allows us to create a new kind of number, negative numbers, right? Integers. So integers can be negative or positive or zero. It's everything that's in this circle right here. Natural numbers, it's just what's in the red circle. Okay, let's keep going. So we're almost at the end of this lesson. I just want to highlight that there are two ways of viewing this expression right here, 5 minus 3. So one way of viewing it is as a subtraction problem. It's 5 and 3, and we're subtracting them. An equally valid way of viewing this is as an addition problem. It's 5 plus, now, since we have integers, right? It's 5 plus negative 3. Now that we can talk about negative counting numbers, we can actually interpret this as an addition problem. So both of these are the same thing. And it may seem sort of trivial at this point, but it does highlight the fact that it's sometimes very helpful to be able to see the same expression or equation or formula, to see it in a couple of different ways. So if you're able to see things in two or more ways flexibly, sometimes it makes problems that if you just see it in this way, it would take a long time to solve, but if you can interpret it as an addition problem, for example, it's much quicker. The solution pathway is much quicker. So I just wanted to highlight that. And finally, last point, if we just want to talk about one way to interpret integers, is as directionality. So for example, let's draw a number line, sketch a number line here, and of course we have our 0 in the middle, and then 1, 2, 3, 4, 5, 6. Let's go up there, and we can do our -1, etc., -3, -4. So here's our number line, right? Later on, we can be adding a vertical number line, and that'll give us our Cartesian plane, our xy coordinate plane. But for now, we're just talking about a number line. So if we think about the equation, 2 times 3 equals 6. One way to interpret it is 2 is sort of, this is all in the we can call this sort of like the positive direction, right? So I always start at 0, and if I have 2, I go over to 2. Times 3, I can think about stretching that length of 2 when we talked about one way of interpreting multiplication is a scaling by a factor. That's definitely one way that we can think about it. If we stretch 2 by a factor of 3, this length right here, we pull it all the way out, and we do end up indeed with 6, right? So that's where that 6 comes from right there. Now, if we wanted to think about what it would look like to do 2 times -3, we can interpret this negative value as switching the direction in which we're going. So again, here maybe it's clear if I can keep this in red. So again, we're starting at 0. The 2 is a positive 2, right? We don't write it, but this is really a positive 2. I go over here to my 2, but then I'm going to stretch it by 3, and that negative is telling me to switch the directions. So I'm stretching it by 3 to 6, and then I'm switching the direction. Oh, that is a 6, of course. I'm switching the direction, and I end up with -6, right? So this right here is another way of interpreting negative numbers as directionality. And that's it for this lesson. So thank you so much for listening. Please don't forget to write down any questions you still have about this lesson so you can ask your instructor. Thanks, and stay safe.